Okay, so in this section, in this lecture, we're going to cover section 3.3, I think it is. And this is on derivatives of trig functions. So let me share my screen so you can see what I'm seeing. So this, yes, 3.3 on the derivative of trig functions. So what we're going to do is we're going to take our two basic building blocks for these trig functions are the sine and the cosine, because we know that the tangent is the this will be the quotient of sine and cosine, and then you have that the other trig functions, secant, cosecant, cotangent, are just reciprocals. So as soon as you know sine and cosine are differentiable, and you know what their derivatives are, you can derive the derivatives. Maybe I should say deduce the derivatives of all the other trig functions. So, for example, if you know the derivative of sine and cosine, you can immediately get the derivative of tangent by using that quotient rule that we learned. We didn't prove it. We're going to prove it once we learn the chain rule. But you can actually get the derivative of tangent by using the quotient rule. So it's nice to view. It's nice that we can view these trig functions as being built from the sine and the cosine. So the question really comes down to whether or not sine and cosine are differentiable. So let's try to get some intuition for this. So let's take this to be our function. Let's try to get some intuition to this as to whether sine, for example, is differentiable. So here's our function. We're going to take x to be in radian measure, as always. So the best way to get intuition is, or a lot of times to get intuition for claims, is through like geometric reasoning or geometric arguments. So the best way to do this is to just get a graph of sine. So here's our graph of sine. And then remember, intuitively, being differentiable means that, or being differentiable at a point means that at that point and at near that point, your curve is smooth. So if this is the graph of sine and we just take any random point and then just trace up onto the curve, yeah, it looks pretty damn smooth right here, right? It's a very smooth function. And in fact, we can work out the derivatives also using the fact that the derivative is the slope of the tangent line. We can work out what the derivative is at some point. We're kind of assuming the derivative exists. We haven't proved it. We are gonna prove it. Well, but just looking at the graph, it's like, yeah, this is a pretty smooth curve. So it's definitely continuous. You can draw the curve without lifting your pen, but it also appears to be differentiable because it's smooth. It doesn't have those kinks or corners or anything like that, or points where you have horizontal tangent lines, none of that nonsense. So we can look at in working on that assumption, we can try to maybe even work out what the graph of the derivative looks like, and it's going to be interesting actually what it ends up being. So like right here, we have at this point 0, the tangent line, slope of the tangent line is 1. At this point right here, pi over 2, the slope of the tangent line is 0. So we can like kind of write down some stuff down. So we can say that at 0, sorry, yeah, f at the 0, f prime is 1. At pi over 2, f prime is 0. And then at pi, f prime of pi, it's -1. And then at, I guess, what is this? This is 3 pi over 2. It's -1. And then f prime of 3 pi over 2 right here. The derivative is 0, assuming it exists. And so we can actually plot these and try to like connect the dots. And when you do that, you'll see that this is the curve you get. See, this is slope of 1, so the graph should be at height 1. At this point right here, the slope is 0, so it should go through the x-axis at 0. Right here, the slope is -1, so the height of it should be, the distance from the x-axis should be -1, and then just repeats, right? Because sine is periodic, so the derivative is also periodic. So it really looks like there's really only one option for the derivative, and then that is that the derivative is just cosine x. And so none of this is proof. This is just building intuition as to what we might think the derivative is. And based on that, we would just like it's reasonable to conclude that yeah, the derivative, if it exists, should be cosine x. And that intuition is in fact correct. So this is, I just wanted to go through the problem in this way because in mathematics, intuition building is very important. Trying to get mental models, mental pictures of problems and phenomena is a very important skill of a mathematician. And so it's always good to have those mental models and those intuitions and those pictures in your mind before you set out to prove something. Because without them, you might not even know what you need to prove. Based on this curve, you might just say, this curve right here, you might say, yeah, it's differentiable. It looks pretty smooth, but I have no idea what the derivative is. But without that analysis that we sort of did here, this like not non-rigorous analysis right here, we can actually sort of work out what the derivative looks like, and we can kind of guess that, yeah, this is definitely going to be the cosine curve. So let's actually go through the calculation. Let's compute from the definition of derivative. So our guess is that if this is our function, then the derivative should be cosine x. So let's try to verify that. We're actually going to run into a problem, and that's okay though, because sometimes your intuition can only go so far. Then you have to confront some sort of technical calculations that require some tricks. And that's where logic and rigor comes in. Then you have to go through and actually deal with these things logically and rigorously. But we're going to do that eventually. But let's see how far we can get into the calculation before we run into a dead end. And then maybe we need to develop some more ideas. So this is just the derivative by definition. We substitute in. So we replace x by x plus h. So we get sine of x plus h. And now here we're going to actually use our addition formula for our trig function. So, if you ever wondered why do we care about these trig formulas, well, here's why. They end up useful. They end up being useful. It's not just some formula you have to memorize to annoy you or anything. They're actually useful. So this thing right here, sine of x plus h, when you use this addition formula, I'll let you look that up if you want to, but this is the formula right here. Sine of x plus h is the same thing as sine of x times cosine of h plus cosine of h times sine of x, like that. So this thing is equal to this thing right here. This is called the addition formula. And now, erase this now. We're on this line, so what we're going to do is we're going to put this term and this term together. So we get this first fraction right here, see the numerator. And then we're going to and then of course you got to divide that by h, and we're going to split the fraction. And then the other fraction is going to have this as the numerator. See, right there. And then divide that by h, of course. So we split the fraction and kind of put terms together. And now we have a sine x here, sine x here. So we can factor that out. And x is fixed now. So this is sort of this is actually a constant with respect to this limit because we're taking the limit as h goes to 0. No x is involved in that limit. And then we have this cosine x here, so we can kind of factor that out. And then what we're left with is this and this. And this is sort of the roadblock we run into, the stone wall, whatever. We got to figure out what these limits are. And it's not terribly difficult to figure it out, but it does require some work. So now we have this product here, we have this product here, here and here. So we can first of all distribute this limit over this sum right here. So that's why we get like a limit here and a limit here. And then, but now we have this product right here and this product right here. So we take the limit of the product. But this right here is just a constant. We're taking the limit of a constant. And same thing over here, limit of a constant. So this just ends up being sine x times limit h as h goes to 0 cosine h minus 1. Oof, I don't know if I'm going to fit that divided by h. And then this is going to be plus cosine of x times, and then what's supposed to go here is limit as h goes to 0 of sine of h over h. Sorry about that. Now here's something cool to note though. So our guess was that our conjecture, our guess was that this derivative should be equal to cosine. And notice we do have a cosine up here. We do have this sign here. So the problem comes down to figuring out what is this limit right here, and what is that other limit? What is this limit? So what is this limit? Let me clean this up over here. I just wanted to write this simplified a bit. So the question becomes down to what is this limit and what is this limit? And based on our guess, we want this sine x term to, we don't want that to be left over, right? I don't know why it keeps erasing all of that. That's really annoying. So our guess should be that this whole limit is 0, and this should be 1. And if that's the case, which is going to be the case, then we'll get the right answer because this whole term right here will die. The sine x will go away, and then all we're left with is this, which is limit of constant, so it's cosine x. So if we can show that this first limit is 0 and this limit right here is 1, we'll be done. Um, so yeah, well, this is what we're going to prove later in this section. So this is sort of a roadblock, but we now have a conjecture. So we have like sub conjectures or sub claims. We want to prove these. So we're going to prove that later at the end of the section. For now, we're going to kind of assume that, yeah, we're going to just assume these are true. And then the limit will, the derivative of sine x will in fact be cosine x. And then let's do some calculations. Yeah, so here we go. Putting all these things together, limit of a constant is just the constant. We're assuming that this is 0, and in fact it is 0. We're going to prove it. So we have 0 here, and then this limit right here is 1, so that's why we have this 1, and then this limit of this constant right here is just this constant right here. So overall we get cosine x. So now we can work through some examples. So we have this example right here. We want to differentiate x squared times sine x. So this is going to be a product of two differentiable functions. So we need to use the product rule. We're using the product rule right here. So when you take the derivative of this, um, I don't really like the way they're doing it. Let's do it over here. So we have y is equal to x squared sine x. So according to the product rule, the derivative of y, dy dx is, you take the derivative of the first function, that's 2x, times the second function, and then plus the first function, don't do anything to it this time, times the derivative of the second function, but we just determined that that's cosine x, so it's going to be cosine x. And then you can just leave it like that if you want. There's not really much more you can do. You can factor out an x, I guess, but that would be unnecessary. At least for this problem, it would be unnecessary. There's no point. Maybe in some certain problems you would have to factor out the x. There's an x here, and then there's a factor of x here. And that's what we got. All right, so now, as they note in the book, if you go through the same sort of steps, the exact same steps, you use the addition formula. So if way up here, we used this addition formula for sine on this to get this step. The only difference is like this will not be a sine, it'll be cosine, this will be cosine, and then you're just going to use the addition formula for cosine, and then you're going to put terms together in the same way, and you get the exact same calculation, and in fact you'll get the exact same limits that show up. Those roadblocks, the exact same roadblocks show up. So you can get this right here, this formula right here. Notice there's a negative in here though. So maybe it would be a good idea for you on your own to go through that and figure out why exactly does that negative come up. You can also probably see that from the graph of cosine. Actually, we have the graph of cosine up here. So let's figure that out. Why are we getting negative? So let's ignore the fact that this is the derivative. We know that this is just actually the graph of y is equal to cosine x, right? So let's think about why this might be negative sign. So at 0, we have horizontal slope. So um, actually, let's ignore, like completely ignore this graph. Let's just look at this graph in isolation. So let's call this g of x is equal to cosine x. And let's kind of get a table of values. So at 0, the function is 0. Okay, that's good because the derivative, I should say, is 0 because it's a horizontal tangent line. So that's good. So sine of 0 is 0. Good. Why are we getting this negative? Well, let's think about this point. So this is, if you draw the tangent line, it kind of goes like this, and it goes up like that. So this looks like a negative slope, and it's going to be -1 actually. So at pi over 2, you get -1. And then at this point, this will be like 3 pi over 2. So this is going to be up like this. This would be like +1. I don't care about this 0 point. I'm not going to worry about that. So this is 3 pi over 2 gives you +1. Now we can kind of see why this is these are the derivatives could be negative. So let me write it over here. So g prime of pi over 2 is -1. And that's going to be equal to negative sine of pi over 2, right? Because sine of pi over 2 is 1. So if you throw a negative on there, you're going to get the derivative. And then let's look at the next one. So g prime of 3 pi over 2 is going to be 1. And if you throw a negative on the sine of 3 pi over 2, you're going to get 1. Because sine of 3 pi over 2 is -1, right? Make sure if you're not sure, pause the video and consult your unit circle. But sine of 3 pi over 2 is -1. And then if you throw a negative in front of it, the negatives will cancel out to give you 1, which is what we're kind of estimating the derivative to be. All right, so that makes sense. So our guess should be that when you take the derivative of cosine x, you get negative, because that's kind of what these calculations are revealing, or these geometric pictures or geometric argument, this intuition, however you want to phrase it. This is all like, there's like two stages of mathematics. There's like the rigorous stage, and then there's the pre-rigorous, and we're kind of like working in the pre-rigorous phase where we're just developing intuition. So all these are non-rigorous calculations. So what all these images, these pictures, these intuitions suggest is that the derivative of cosine should be equal to negative sine x. And then if you, in fact, go through all the same calculation we did for sine of x using the difference quotient definition of derivative, you will see that you get this, in fact. Now, as I said at the beginning, once you know the derivative of sine and cosine, you can get the derivative of the rest of the functions, the trig functions. In particular, you can get the derivative of tangent. So tangent is by definition, or one way of thinking about it. This is the nice thing about these trig functions is that there's just multiple perspectives, and sometimes one perspective is more useful than another. So we're going to use the perspective that tangent of x is this ratio right here. So you can take that to be your definition, or you can just take it to be like a consequence of your definition. But in any case, we're going to use the fact that tangent of x is this ratio right here, and we know the derivative of sine and cosine. So we just apply the quotient rule. So I think they're going to do it differently than me. So I'm going to do it on the side because I think I memorized the formula differently. So let's do it on the side over here in real time. Anyways, it's always good to do mathematics in real time. So it's definitely good to read through the book, but it's always a good idea to see others do mathematics and to do the mathematics with them. There's something like really visceral and tangible about doing mathematics, like actually writing the mathematics out. It makes it like more dynamic in a sense. There's a whole lot of like psychological aspects of learning mathematics that I can't even pretend to understand, but it's definitely a good idea to do mathematics. That's the only way to learn mathematics, which do mathematics is the way to learn mathematics. So what is this derivative? So we're gonna take the derivative of the top. So we're gonna take, so it's the way I remember the quotient rule is that you take the derivative of the top, and I won't actually write that out, derivative out. I'll just leave it as d derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared. So cosine of x squared. So the derivative of sine x, we remember that's going to be cosine. So it's cosine x times cosine x minus sine x. And then we determine that the derivative of cosine x, or I kind of just said that the derivative of cosine x is negative sine x. This is all over cosine squared x. And now what we're in the numerator, we have cosine squared x, and then there's a negative here and a negative here, so we get plus sine squared x over cosine squared x. And the numerator is 1 by the Pythagorean theorem, right? So all these formulas are useful. They're not just formulas that math teachers or professors want you to memorize to make your life more miserable. So then this is going to become secant squared x, and that's exactly what we have over here. So the derivative of tangent x is secant squared x. So this is sort of why we care about these inverse trig functions, because they naturally arise as derivatives of the tangent function. So you really don't care about the inverse trig functions a whole lot in and of themselves. The only reason why we care about these inverse trig functions is, for example, they arise as the derivative of trig functions we do care about. We really just care about sine, cosine, and tangent. So this is kind of one reason why we single out those inverse trig functions, because they pop up. It's not, we don't just define these inverse trig functions or reciprocal trig functions. Sorry, I meant to say reciprocal trig functions, not inverse trig. That's a different thing. So we don't just define reciprocal trig functions to make your life more miserable. They really actually show up naturally. So if you care about derivatives, which you should, because if you care about science, which is all about how things change in time or with respect to other things, you got to care about derivatives. And if you care about the derivatives, if you care about those, you got to care about derivatives of these functions, and in a sense, you got to care about reciprocal trig functions. So all these things are very connected. All right, so now we can get the derivatives of the remaining trig functions, and you just do this using the quotient rule, all just repeatedly. So here is this table right here. Here's a complete table of all the trig functions, the derivatives, I should say. All right, so let's see. Here's another example. So we have this function right here, and we want to differentiate it and then find out where's the graph have horizontal tangent lines. So remember, horizontal tangent line means zero slope. So that means set derivative equal to 0. So let's look at what they do here. So we have um, the quotient rule. So they take the derivative of the top times the bottom. They write it backwards, that's all. I don't write it this way. And then the top times the derivative of the bottom. All right, so the derivative of secant, according to this table, is secant x 10x. So we have this thing in parentheses right here, times the derivative of secant, which is secant x 10x. And then we have secant x here, and then the derivative of this thing, well, we know derivative of 1 is 0, and we just proved that the derivative of tangent is secant squared. So overall, we have a factor of secant right here, a factor of secant right here, so we can factor that out right here. And then what we're left with is, let's see, what are we left with? Oh, so we have this tangent right here that distributes to this tangent and then this one. So we have tangent x squared, and then finally minus this secant right here. So minus the secant right here. So that's what happens when you factor out that secant x and simplify the numerator. And in the denominator, remember you square the denominator of this thing right here. And then let's see, they're using a trig formula somewhere, I guess. Oh, this right here, so we can eliminate this secant right here. So in the numerator, let's just write the numerator out. So we have tan without the secant. So tan x plus tan squared x minus secant squared x. And then secant is the same as tan x plus 1. So this is going to be equal to tan x plus tan x squared x. This will be minus tan squared x minus 1. So this is going to be equal to tan of x minus 1. Now, now what we need to do is set the derivative equal to 0. And what the setting that equal to 0 is the same thing as setting the numerator equal to 0. So we set the numerator equal to 0. So it's going to be secant times tangent x is equal to 0. So that's going to imply that either secant x is equal to 0 or tan of x is equal to 1. But as a note in the text, this can't happen. Secant x is never 0. So the only way we can get derivative is equal to 0 is if tan x is equal to 1. And the tan x equals 1 occurs when x is of this form right here. X is of this form. So that's where the derivative is 0. All these points, so an infinite number of points, because n is just any integer, and hence that's where we have horizontal tangent lines. So here's a graph of the function right here. This is a graph of secant of x over 1 plus tangent of x. And we get, well, they didn't really label the graph, but I'm guessing that this right here is probably pi over 4. I guess this would be maybe 5 pi over 4. So I'm just like, so you have x, you have this parameter n. So you have pi over 4 plus n pi. And so like when n is 0, you get pi over 4. When n is 1, you get pi over 4 plus pi, which is equal to 5 pi over 4. And then you get a bunch of other values going out to negative infinity and then positive infinity. They only just showed 2 of these values on the graph where you have this horizontal tangent lines. So trig functions are important. They're used in modern real world phenomena, so you can model vibrations, waves, elastic motion, periodic motion, motion on a spring. There's a quantum oscillator that's really important, and that is modeled using periodic motion. So a lot of interesting, important applications. All right, let's see. So just gonna skip these. All right, so now let's just work on these limits. So let's go back to the problem we were dealing with. Remember, we wanted to prove. So we're gonna phrase it. The limit we were looking at was phrased in terms of h, but we're just gonna change a variable to theta, which is not a big deal. So we wanted to prove. Let me just write on the side. Actually, let me scroll back up to the top so you can see all the way to the top. So we have these two limits we need to prove. So we're gonna phrase them both in terms of theta. All right, so let's go through the proof. So what we have, so we're gonna take a limit as theta goes to 0. So it's perfectly fine to assume that a theta is gonna be close to, first of all, a theta needs to be close to 0. So we can just assume it's between 0 and pi over 2. Meaning, if we're thinking about theta as an angle, that's going to be an angle in a right triangle, right? So here's this triangle we're going to set up, and we're going to use, we're going to like kind of inscribe this triangle right here into a unit circle. So we drop a line down to get a right triangle like that. And then this angle is going to be theta. So this is inscribed in a circle. And we have a lot going on. So I'm going to try to explain everything in detail. So we have a circle. We have this sector right here, this blue curve right here. it's just going to be this arc length of length AB, and so there are going to be two. We're to prove this limit right here. We're going to prove um, two things, and we're going to use two things. So we want to show that we're going to want to show this inequality, and then use squeeze theorem. So here's an important application of the squeeze theorem so it's kind of cool that you need to use the squeeze theorem to prove that sine and cosine are differentiable. So we're gonna show that this inequality holds, and then use the squeeze theorem to do that. And once you see that, when you get this inequality, you can see the squeeze theorem takes care of it, because what happens when theta goes to zero? So now let theta go to zero in this inequality. Well, as theta goes to zero, one goes to one, right? But as theta goes to zero over here, it goes to one. So this thing gets squeezed between one. So that's why this limit has to be what it is. So the squeeze theorem is a really important theorem, and we're going to use it to prove this limit. All right, so first of all, um, by definition of radian measure, we have that the arc length of AB just is the angle. So when you measure in radians, when you rotate an angle in radians out, is by definition the arc length on the corresponding circle. So this angle right here is equal to this arc right here, this blue curve that's angled, not straight line. Um, and then also what we have is this equation holds here. Well, why does that hold? Well, let's look at the triangle. So we have sine of theta is equal to is going to be equal to adjacent opposite. So this black line right here, the length of it, so B over C, divided by the hypotenuse, which is the length of OB. But we're on the unit circle, and B is a point on the unit circle. So this length right here is 1. So the length of OB is 1, so it's going to be BC. So sine of theta is equal to BC. Now, also from this diagram, we can see that the length of AB, this straight black line right here, is, first of all, it's going to be bigger than this black line right here, BC. So the length of AB is going to be bigger than BC, the length of BC, but it's also going to be less than this arc length right here, of AB. So that's why this inequality holds. So you can see this arc length right here is kind of trapped between this arc length right here is trapped between this sorry, the line AB is trapped between this line and this arc length. So that's why we get this inequality right here. But we know that arc length of AB is just theta. And we know that BC is equal to sine of theta. So what this implies is that we get sine of theta is less than AB, and that's less than theta. So that's why we get this right here. And then if you divide by theta, of both sides by theta, which is fine, because we're assuming that theta is between 0 and pi over 2, so it's a positive number. We're not going to change the sign of the inequality. When you do that, you get this right here. And that's 1/2 of the inequality we need. We got this part of the inequality. Now we just need this other half, and then we can just apply the squeeze theorem to prove the limit. Whoops. All right, so now let's shift gears a little bit to get the other inequality. So first of all, so let me erase some of this mess over here, so it's a little bit clearer what's going on. All right, so now we have the tangent line. Well, I don't really care about tangent lines, actually. Anyways, so what we have is this inequality right here. Why is this true? So we have this arc length right here, this blue curve, is going to be less than, yeah, it's going to obviously be less than the length from the length of this red line, A to E, and the length of this red line, A to E. It's going to be just a bit bigger. So that's why this arc length is a bit smaller than the sum of these two lines on the polygon. So we have this circumscribed, sorry, circumscribed polygon. You can which you can see in this figure right here, B. So the length of the line from A to E and B to E is going to be just a bit bigger than the arc length. But the arc length, remember, is by definition theta. So theta is going to be equal to arc length from A to B, which is going to be less than the sum of the two sides of the polygon. It's a little bit less based on the drawing. Now the EB, the length of EB is going to be the same as ED and you can see that from the diagram here. The length of this side right here is the same thing as the length of this side, just extended up. So it's the same length. And then so now we can replace this with this. And now the length from AE to ED, what is that? Oh, sorry, when you add these two together. So AE, and then to ED. That whole thing is going to be, so if you take this length from here to here, and then add the length from here to here, you get the length of the whole line, which is A to D. So this sum right here is equal to the length of A to D. And then why is it equal to this though? Well, that's because of just the right triangle. So let's look at tangent of theta. So tangent of theta, when you consider this whole big triangle, go from here all the way up to D. So from O to D, and then from O to A, that is going to be the opposite. So the length of AD divided by the adjacent, the length from O to A. But A, the vertex A is a point on the circle. So the length from O to A is going to be 1 because that's the radius. We're talking about the radius of 1. So tangent is just going to be the length of the segment from A to D. So the length of the segment from A to D is going to be OA times tangent of A. But as I said, OA is just length 1 because we're talking about unicircle. So ultimately, what we get is that theta is less than tan theta. So theta is less than tan theta. But what is tan theta? It is tan theta is by definition sine theta over cosine theta. And now I divide both sides by cosine and divide both sides by sine theta. So that gives me or sorry, I multiply both sides by cosine theta and divide by theta, and I get cosine is less than sine over theta. So that's the other half of the inequality. But remember, we also determined that it was less than 1. So that's how I would get this. And now when you take the squeeze theorem, we know that the limit of 1 as theta goes to 0 is 1. And we know that the limit is of theta as cosine, sorry, as we know that the limit of cosine theta as theta goes to 0 is 1. So by the squeeze theorem, we can conclude the limit. Now notice here's a little kink. The limit as theta goes from the right of this thing is equal to 1. So we can pretty much have everything. And the reason why it's a right-hand limit is because remember, we assume that x is between 0 over 2, but that's not a problem. The reason why it's not a problem is because this function here just so happens to be an even function, right? So if you do sine of negative theta, over negative theta. So you replace theta with negative theta. You now use the fact that sine is odd, so you can pull this theta at the negative out of sine, and now you can cancel the negatives. You just get the function back. So in other words, when you replace theta with negative theta and do this manipulation, you just get the function back. So that's why this is an even function. So in other words, now we have this right-hand limit of this thing is equal to 1. If you take the left-hand limit as theta goes to um as theta goes to 0 from the left, you can switch all the negatives to make it a positive and just use this limit right here. So let me make that a little more explicit though. So in other words, this is what I'm saying. So you take alpha equal to negative theta, and then so for theta less than 0 but close to it, say close to 0, and then so now as theta approaches 0 from the left, so we already have the right hand limit, so let's do the left hand limit. Theta approaches 0 from the right because theta is going to be a small negative number and alpha is equal to negative theta, so you make it positive. So theta approaches 0 from the right, alpha approaches 0 from the theta approaches 0 from the left, alpha approaches 0 from the right. So that means when you take the limit as theta goes to 0 from the right of sine theta, it's going to be equal. Now use this equation to substitute. It's going to be the same as the limit as alpha goes to 0 from the right of sine of negative alpha over negative alpha. But as we noted, this is an even function, so you can just cancel kind of like well, you just go through the same steps that we just did. So let's go through that. Just pull the negative out because sine is an odd function. They cancel. I get sine of alpha over alpha. But this limit right here we just proved is equal to 1 right here. We just used different symbols, so this is 1. So now what this shows is that if you take the limit, if theta goes to 0 from the left, you also get 1. So left and right hand limits exist. So therefore, this overall limit exists and it's equal to the common value. All right, so that's that. There's this other one. I guess I'll leave this one to you. This one is not, I promise, not as hard. This limit. It actually just you kind of use this limit to prove this one right here. So the trick here is, yeah, you start with this limit. There's not any geometry involved. I know the geometry and the other one is kind of a little complicated, but this one just is based on the other limit. You multiply and divide by this, like here, and then you do the foiling out, you get cosine squared theta minus 1. Well, by the Pythagorean theorem, that's going to be negative sine squared theta, right? By the Pythagorean theorem, you can pull the negative out of the limit. And then this fraction can be written as a product of two fractions. So you have two factors of sine. So one in this fraction, put the other in this fraction, and then put the theta here and then the cosine theta here. Now this limit right here, we know is 1 or negative 1, right? That's the one we just determined. This limit right here is a continuous function of theta, and it's continuous at 0, so just plug in 0. So this limit was a bit easier once you know the other limit. So here's an example of using one of these limits. So besides using these limits to compute derivatives, you can also use them to compute other limits. So here's the trick. So you want to compute this limit right here. Well, it's not quite like sine x over x. We get a 7x, we get a 4x, but that's not a problem because what we can do is we can factor out the 7. This is kind of, let me actually write what they're doing. So what they're doing is they're going to factor out the 4, I should say. So it's be like 1/4. And that's close to what we need because it's remember it's sine of some variable divided by that variable, right? So we need a 7 in the denominator. So I'm gonna multiply and then divide by 7. So notice I did not change anything. This thing does in fact equal this. So that's how they got this equation here. And then you can just take the limit. So you're gonna let theta be equal to your 7x. And so as x goes to 0, theta goes to 0. So using this equation right here, or the limit we derived right here, I guess this one right here, we can do some substitutions. So this thing right here is 7/4 times 7x over 7x, sine of 7x over 7x. And then the 7/4 just kind of goes along for the ride, but we let theta equal 7x. So that's why we get this. Well, we just determined that this limit is 1, so it's 7/4 times 1, so 7/4. And then there's this other example. I'll let you go through these examples if you want, kind of basically using the two limits that we just proved, which are we proved them first to compute derivatives, but you can use them to compute other limits. All right, that's all for today.